Okay, so I'm going to speak briefly about matrix algebra, at least the stuff we need. So a matrix is a bunch of numbers. So it comes in many applications. So an array of numbers arranged in a rectangular form. Okay. But the one I am interested, so this has got properties, eigenvalues, eigenvectors, determinant, etc. Right. So the determinant of a matrix, if a matrix is small, 2 by 2, then you know it is AD minus BC, for example. But you can also define the determinant of the. So I'm assuming you have some knowledge. And what I want to talk today is about non-negative definite matrices. Matrices. So what that means is if you have a matrix and if you multiply by a vector on this side and the same vector on this side, so this will, if this is x, this is the transpose of x. I'm going to write it like this. So of course the size is clear. I mean, I'm talking about n by n matrices. So if this is n by n, then of course this, what will be the size of this vector? Anyone? If the matrix is n by n, so what will be the size of a vector on the right side?
1 by n.
N by 1, not 1 by n. Right? N rows and 1 column. And this will be, of course, 1 by n. So the whole thing will be 1 by 1. So that will be a scalar b. If this scalar is non-negative, remember I didn't say what, any x, you take any arbitrary x. If this scalar is non-negative, then this matrix is called non-negative. So the property is not on the vector, it's a property of the matrix. Because you can change the x to any y, this is still non-negative. If this is strictly positive, we call this matrix to be positive. We will see why it is called a non-negative definite matrix. So as an example, take this matrix A. So let's see whether it is non-negative. So we'll multiply by x transpose Ax. This is not the way to do it, but we'll do it. So let's say x is, so you have 2, 1, minus 1, 1. So this is, what is it, x1, x2. So this is x1, x2, this manner. So if I multiply this, look here, first row into first column, that is 2x1 minus x2. First row into first column, this is minus x1 plus x2. This multiplied by x1, x2. So this is just to show you. Remember, x1 and x2 are arbitrary. So x1, x2 multiplied by x1 minus x1 plus x2 multiplied by x2. So if I expand, you get 2x1 squared minus x1, x2 minus x1, x2 plus x2 squared. Notice that this can be written as 2x1 squared minus 2x1, x2 plus x2 squared. This is positive because I can write this as, so look at here. So this thing which is arbitrary, when I multiply all this, turns out to be this. It doesn't matter what the values of x1 and x2 are. This will be always in fact a positive, because if I take x1 and x2 to be, the only case this will turn out to be 0 is when if I take x1 and x2 both to be 0. So for, I mean, everything is real here. I'm just showing you a real case. So this is a property of the matrix, not of the x1 and x2. X transpose AX is positive for all x, vector x not equal to, if you don't take x to be completely zero, this will be, so that's what we mean by a non-negative matrix. So this will be a positive definite matrix, is positive definite. Remember, then there are cases where these a matrix with the positive entries like 1, 2, 3, 4. This is not a, this is called a positive matrix because all the entries are positive. This comes in probability matrices. For example, 0.1 like this. We are not dealing with this now. There's also a lot of theory on this. So we are dealing with matrices of this type. Why is this important? Look at our problem. So x of t is a random vector. Let's say these xi's come from a stochastic process. So remember, this is, so we sample a stochastic process at t1, t2, etc., tn. We get a bunch of random variables x1 through xn. You put it in the vector form. Then if you look at the covariance matrix of that vector, that's the same as x, so call this R, capital R. So R is an entry is here going to be xi, xj. So this is nothing but expected value of xti multiple. So I'm going to write star here. So this will have star because in general this could be complex. xti, xtj star. But this is nothing but the covariance matrix autocorrelation function evaluated at ti comma tj. I think I showed in class that this matrix has got this property. So let me show you it quickly again. So I take some arbitrary vector y. I don't want to take x is here. So, or arbitrary vector a, and I multiply by a. So a is like this. Some bunch of numbers, not random variables, bunch of numbers, a1 through an. So this is the same as a transpose. So remember, this was x transpose a. A is a constant, not random, so a goes inside the expectation. So now let me call this to be y. Or let me call this to be y. So this will be y star. You see that? Because y is a star x. A star is this way, x is this way. So y star is, remember, this is x star, y star, x star, a double star, that's this. So that's this. So y is a scalar, look at it. N 1 by n multiplied by n by 1. This is a scalar. So this is simply expected value of the square of a new random variable. Y is random variable because x is random. So that's the same as y squared density function of y dy. Of course, that's going to be non-negative. So this matrix is non-negative, a non-negative definite. That's why our interest in that. So I'm going to talk about non-negative definite matrices. Any questions? Somebody talk back to me. I want to make sure you can hear me. Anybody there?
Oh,
Yes, Professor.
yes.
Any questions?
Professor, like you mentioned, the expectation is a covariance matrix. So, how it could be?
What do you mean? Tell me what you are trying to answer. Say it one more time.
Yeah, Professor. So from the definition of R, you have you have an expectation matrix times a vector. So how it could be a covariance matrix?
Where is the vector? This one?
X naught. Ex to the ti times tj.
Oh, you mean here?
Yeah.
No, but look at this. This is not a vector. I'm saying this matrix, let's see here. This is a matrix, right? And its ijth entry, this is the ijth entry of this matrix, is expected value of xi xj. Xi means, that's what I'm explaining here. Xi is x of ti. Remember, x of ti is a random variable multiplied by another random variable. So this whole thing is a random variable. Take the expected value. That's what I'm going to call Rij. I don't have to call this Rij. Rij is a number. Then I create this matrix with R11, R22, etc., Rn. Is it? We are going to talk about this matrix as a whole.
I see. I see. Yes, Professor. Thank you.
Right. So this entry, so I'll write it in, just make sure. R is this matrix. Here you have R11, R12, etc., R1n, R21, R22, etc., R2n, Rn1, etc., Rn. So the ith here will be Ri1, etc., Rij, Ri. So I'm going to take this value. This is expected value of xti, xtj star. That's what it is. So that's the expected value of a random variable. I'm going to talk about this matrix. That's what it is. Yes?
Yes, Professor. Yes.
All right. I already showed you that this is a positive definite matrix. So I'm going to write it like this. It's a non-negative definite matrix. Because the proof is here. If you multiply by any arbitrary a vector on the same vector on both the sides, then you get this. Is this clear? Is this clear? Proof.
Professor, is the star only stands for transpose, or is conjugates and transpose?
A conjugate transpose.
Okay, thank you.
All right, so right, so look at here. If A, just to make sure, if A is A1, A2, etc., An, when I say A transpose means this way. So this is n by 1, this becomes 1 by n, and this is A1 star, A2 star, etc., An star. So this star stands for both conjugate and transpose. And of course, if it is not complex, then star stands for just transpose. Transpose means a row becomes column. All the rows becomes columns. Conjugate means you plus conjugate it. So if you multiply A star and A here, this will become a scalar. Okay. So is this proof clear? That's what I'm asking. Is this proof? So this is a positive definite matrix. Tell me yes or no.
Yes, Professor.
All right. Very good. So let me proceed to. I don't know whether. So we will do eigenvalues, eigenvectors, and singular value decomposition. Up to there, we will see. So for any matrix, maybe you have heard this. This is what we mean by eigenvalue. If you can solve for an x is a vector, you want to find a vector such and a scalar such that this equation is satisfied. So let me show you example. So we'll take the previous example. So we want to solve for this equation. So notice here you have 2x1 minus x2 equal to lambda 1 x1. So 2 minus x1 plus x2 equal. So you can lambda 2. So we need to lambda 1 x2. So we need to solve for this. So so the way to do this would be, this is the same as saying that a minus lambda I. So if multiplied by xi should be 0. So notice that if there is such a lambda, then this equation must be 0. And if this vector is non-zero, that means this determinant must be singular. I mean, that the matrix must be singular, right? You can see from here. Because if the matrix is not a singular, you can multiply by inverse, then xi is, comes out to be 0. So if you want a non-zero vector, then this must be singular. That means you clearly see that all the eigenvalues satisfy this equation. By this simple argument. So in our case, that will be 2 minus lambda minus 1 minus 1, 1 minus lambda. So if I take the determinant of this equal to 0, that's 2 minus lambda multiplied by 1 minus lambda plus 1 equal to 0. So what do you get? Lambda squared, right? What is it? Minus 3 lambda plus 2 plus 3. So you can find the two eigenvalues is equal to 3 plus square root of b squared, which is 9 minus 4ac over 2. So this comes out to be 3 plus minus j square root of 3 by 2. So those are the two eigenvalues. Eigenvalues happens to be complex here. So let me, did I make any mistake? Let me see here. Lambda squared minus 3 lambda plus 2 plus 1, 3 minus b plus minus b plus minus b squared minus 4ac any mistakes?
Professor, it should be minus 1, not plus 1.
Here?
No, left, yeah.
Why?
Because it's AD minus BC, yeah.
Yeah, that's right. I thought I made a mistake somewhere. So let's see, the lambda squared 3, okay, 2 minus 1. So this is 1, right? Yes? Yes. 2, yeah, but plus 1, right? So the equation is lambda squared minus 3 lambda plus 1 equal to 0. So let's find out the two roots. B plus minus square root of 9 minus 4, yeah, this is correct, equal to 3 plus minus square root of 5 by 2. Notice that both the roots, square root of 5 is less than 3. So lambda 1 is 3 plus square root of 5 by 2, that's positive. Lambda 2 is 3 minus square root of 5 by 2, that's also positive in this case. That's how you find the eigenvalues. Once you have the eigenvalue, take one of them, put it here, and you solve for x1 and x2, and then do it for the other one. Okay. So in particular, let me talk about matrices like this. Remember, our covariance matrix has this property. So I'm mainly interested in so let's say this is expected value of x transpose. So if you take the transpose of this again, you get back the same thing. So this is, we know that this is non-negative definite. So all such matrices are, this property is called symmetric or Hermitian conjugate. Now let's look at its eigenvalues, the property. So let's say ui is an eigenvalue and lambda is an eigenvector. So remember, eigenvector is scalar and eigenvector, this is an eigenvalue and this is an eigenvector. So I'm going to show you the properties of eigenvalues and eigenvectors for a non-negative definite matrix. That's the first thing. Then we will go into singular value decomposition, which you should know. So the number one thing, I'm going to show that all the eigenvalues are non-negative and all the eigenvectors are orthogonal. That's what I'm going to show first. These two properties I'm going to show. So So let's look at ui star or ui. Anybody? Remember, we are starting with, this is a non-negative matrix. So what will be the value of this? Anybody? If you multiply the same R with the same vector, remember we already said this is the, here. For a non-negative matrix, this value, for any A, this will be non-negative. So this will be non-negative, right? So this is going to be ui star. You have to watch the proof carefully. Now I am going to substitute RUI, but look at here, RUI is lambda IUI, so lambda IUI. Lambda is a scalar, so that goes outside. So this is UI star UI. But this is simply the norm squared of UI. So you get lambda is UI star RUI over UI star squared. But the numerator is positive, non-negative, this is positive, so the whole thing is positive. So the first observation is very interesting. All the eigenvalues are non-negative. Any questions on this? Otherwise, I'm going to move on. So if I take the second property is if lambda and lambda I and lambda j are unequal. So this means, of course, the lambdas can be zero. If all the lambdas are positive, we call the matrix to be a positive definite matrix. But let me show that these eigenvectors are orthogonal. They are like this. So how do you prove this? So let's take, remember, RUI is lambda IUI, RUJ is lambda J UJ. We know that lambda is real. So these are real and positive. That's what the previous statement says. Lambdas cannot be complex. Look at here. Lambdas cannot be complex. Lambdas are real and positive. So if this is zero, lambdas are somewhere here. So both lambda and lambda j both are positive, non-negative. So I'm going to look at this expression, uj star RUI. But we know that RUI is lambda I. So this is lambda I uj star ui, because I pulled RUI is lambda I ui. I pulled the lambda I outside, so you get this equation. On the other hand, I can also write this as R star uj star ui, right? Because a b star is b star, a star. R has the property that R is R star. That's what we start with. So this R star is the same as R. So that's R uj star ui. But R uj, look at here. R uj is lambda j. So that's lambda j uj star ui. But lambda is a real, a number like 2. So star has no meaning. So this is simply lambda j multiplied by uj star ui. So look at here, I can write this as lambda j uj star ui. These two are equal. So their difference must be 0. So you have lambda I minus lambda j, uj star ui is 0 from here. But lambda, if lambda and lambda j star are not 0, this cannot be 0. So this must be 0. So we get uj star ui is 0. So they are orthogonal vectors like this. These are vectors. Okay, any question with respect to the proof before I proceed? You need to speak up. Anybody? Hello? Are you there?
So Professor, for the last fourth line, well, basically, like I think if we consider as a matrix, we can do the position changing, like from the first, yeah. But meanwhile, like, cause we can also like transform from a matrix to an eigenvalue.
No, hold on. Only this is matrix. These are vectors. Yeah. You understand? So RUI is lambda. Look at the proof. RUI is lambda I. Where is it? Lambda I UI. Lambda is a scalar, so it goes outside. You get this.
Yes. Yes.
And so what is your question?
I mean, just to confirm, like, just because we can also transform from the matrix to an eigenvalue times the vector, thus, like, we can transform the position of.
Yeah, because this is a vector, this is a vector, right? R multiplied by UI will be a vector, right?
Yes.
Yeah. So that's we are using the eigenvalue property to derive this. So the whole question is the eigenvectors are orthogonal for a positive definite matrix. Okay.
Yes, Professor. This proof is beautiful. Thank you so much.
All right, very good. So I'm going to write. So we have this equation: RU1 equal to lambda on U1, RU2 equal. So we can, the way I told you yesterday, you can find all the eigenvectors and the eigenvalues this way. Remember, the size is n by n, so there will be n eigenvalues and n eigenvectors. It's possible some of them are zeros, etc. But nothing can be less than zero. So all the eigenvalues are, so if all the eigenvalues are, there will be two cases. If all the eigenvalues are positive, then we call R to be positive definite. If some of the eigenvalues are non-negative, I mean, some of them are also going to be zeros, then we call R to be non-negative definite. So, but I'm going to write it like this. Now I can arrange this in a matrix form. So I'm going to put U1, U2, etc., UN equal to, so if you arrange it, this you can write this in this form. Lambda 1, lambda 2, this is a diagonal matrix. Here it's going to be U1, U2. Why am I doing this? This matrix multiplied by the first vector is going to be this matrix multiplied by the first vector. That will, you will get this equation. This matrix multiplied by, so RU2 will be this matrix multiplied by the second row. So that will be lambda 2 U2. It will just pick up that, etc. So I just conveniently rearrange. So this is a matrix U. This is a matrix U. So remember what U is. U is a matrix consisting of a vector, the eigenvectors U1, U2, etc., UN. These vectors are orthogonal. We already proved it in the previous slide. So if you take UU transpose, you can see that this will be this vector multiplied by its transpose. So that will turn out to be identity equal to U star U. So we call U to be a unitary matrix. Okay, so U is a unitary matrix. This is a diagonal matrix by construction. So this equation now reads RU equal to U lambda. I'm going to call this to be lambda, this whole matrix. But then U has this property. So I'm going to multiply by RU, U star here. So this equal to U lambda U star. But U star, look at here, is I. So we get this expression. So this is called the unitary decomposition of a covariance matrix. So let me go over this again. So what we have just shown is using the eigenvalues and eigenvectors, you can rewrite R as U lambda U transpose. U is all the eigenvalues. So I'm going to sort of, any questions before I move this? Anyone? So what we have said is RUI equal to lambda I UI. And then R equal to U, and if I put U to be U1, U2, etc., UN, R equal to U lambda U star, where U has the property it is orthogonal, and lambda is a diagonal matrix whose entries are non-negative. So this is called the eigenvalue decomposition of R. You should read up. Let me get, hold on, let me bring in 2 books so that you can note it. Okay, I'm not advertising for books here, but this is a good book. Matrix Algebra by Horn and Johnson. And this is also a good book. Theory of Matrices by Lancaster and Tismanasky. L-A-N-C-A-S-T-E-R, Lancaster, Tismanasky. This is a popular book with programs and so on inside. So Goulam and Van Loon, matrix computations. GOLUB. And I like this book. This is a small book, but once you know something, this is useful, lot of resource. So this is Survey of Matrix Theory and Inequalities by Marcus and Mink from Dover. Anyway, let me continue with this. So we'll use this result from time and now. You can also write this as sigma Ri Ui Ui prime. If you expand this, these two are the same expression. I equal to 1 through n. As I said, so remember the lambdas being a positive numbers, non-negative numbers, you can always arrange them in this order. There's no, because these are non-negative numbers, so of course they can be ordered. It is true that some of them can be equal, and also it's true the last few of them can be zeros, in which case you call the matrix to be singular. So R is, the determinant is going to be lambda 1, lambda 2, etc. lambda n. So of course, if any one of these, if these eigenvalues are 0, then a determinant will be 0. If R is 0, then R is singular. And that will also mean that some of the towards the end, some of the because these are arranged in order, some of the eigenvalues could be 0. Maybe the last one, maybe, and the rank of R, as you know, is number of non-zero eigenvalues of R. So you count here. If all of them are non-zero, then it is full rank. If some eigenvalues are 0, then let's say the last one is 0, then the rank is n minus 1, etc. So you can also use this property. So if the determinant of R is not 0. In other words, if it is full rank, then R inverse is also this is true, because look at here, R inverse is summation, one is lambda I ui transpose, the other one is on, I will take it on J, one is on J, 1 over lambda J uj transpose from here. So if I cross multiply, this is double summation lambda I over lambda J ui transpose uj transpose. But remember, if I is not here, if I is not equal to J, this is 0. 0 if I is not equal to J. So this double summation comes out to be only for I equal to J, in which case this cancels and you get ui, this get I equal to J. So ui transpose I equal to 1. So that you can write it as in this form. But that will be I, because ui transpose is summation I equal to 1 through n is this. So you know that this is the correct form for R inverse. So once you have the eigenvalues, you can rewrite the eigenvectors also. Now let me, we may not need it, but let me do this. This you hear in image processing, all this, so you should know what this means. So remember, so far I discussed positive definite matrices. Now singular value decomposition is for any arbitrary vector, any arbitrary matrix M by N. I want you to understand, this is not positive definite. I am going back to just take any arbitrary matrix. So the question is, how can you rewrite this? That's the singularity. So it's a clever method. So first let me take A star. See, if this is a positive definite matrix or non-negative definite, because R equal to R star, etc. So this is non-negative definite. Any matrix multiplied by its, why is this true? Because let's take X transpose Rx, that's X transpose A transpose X. But this is a vector Y, this is a vector Y transpose, so this is Y squared, so that's positive. So any matrix, from any matrix you can create a non-negative definite matrix. So now let's use these properties. If A star is non-negative, we can write A star in this form. So let's say lambda I is an eigenvalue of ui is an eigenvalue of A star. I'm going to write it as ui squared. You will see the reason. Actually, the reason is pretty clear. If it is non-negative definite, all the eigenvalues are positive, non-negative. So I can clearly write it as lambda I squared if I want. Remember, A is given, so you can form A star and you can find out the eigenvalues ui. So you have these eigenvalues I equal to 1 to at the most equal to A star is m by n, so up to m. So I'm going to define Vj to be, I'm sorry, Vi to be 1 over lambda I A star ui. So let's go here again. I'm going to look at the eigenvalues of A star, and then I'm going to define Vi to be 1 over lambda I A star ui. But remember, anybody remembers UIs are orthogonal. Ui is orthogonal to Uj because This is a non-negative definite matrix. We are only interested in A. I am not interested in A star, but this is where I'm going to start, non-negative definite. So I'm going to define, I'm going to show that these VIs are orthogonal. So let's look at VI, Vj star. So that's going to be 1 over lambda I, A star, Ui. Then you have 1 over lambda j, A star, Uj star. So because of this star, this reads lambda I, lambda j. Yeah, I mean, this is, so let me complete it. A star, Ui, Uj star, A star. So I'm going to do to show this, it's best to do the other way. So all this is V. I'm going to do Vi star Vj. This is, and I'm going to, if this is 0, then they are orthogonal. So Vi star is 1 over lambda I, A, what is it, Ui star. Remember, lambda is a real multiplied by Vj. That's 1 over Vj, A star Uj. So this, of course, I can collect it as Ui lambda I, lambda j. This is going to be, look here, this is going to be Ui star A star. So this is Ui star A star. I'm sorry, Ui star A star. I forgot a star here. There was a star here. So because of this star, this is Ui star. So Ui, I'll write it here, Ui star A. So this is lambda I, lambda j from here. Then Ui star, then A here, A star here, Uj. But look at here. A star Ui is lambda squared Ui. So A star, you take this equation. So A star Uj would be lambda j squared Uj. So lambda j cancels. So you get lambda j over lambda I, Ui star Uj. But these are orthogonal. Why? Because here, U's are the eigenvectors of A star. So Ui is orthogonal to Uj. So we get the conclusion that if I equal to j, you get 1 if I equal to j. And if I is not equal to j, this is 0. So these vectors are orthogonal. So now going back here, question is how many eigenvalues will this have? Suppose it may not have all the m of them, depending on its rank of A. So let's say you only have lambda 1, lambda 2, etc., lambda r greater than 0. So only it has r, the rank of A is r, the rank of A star is r, rank of A star A is r, etc. And so you have so we have lambda 1 and lambda 2. We can order these things, lambda r greater than 0. And you have u1 through ur, which are orthogonal. We have v1, v2, etc., vr, which are also all orthogonal. See, if you have, for example, in 2 dimension, if I have 2 vectors which are orthogonal, I can find a third vector which is orthogonal to each other. So we are going to fill up this eigenspace with remaining orthonormal vectors. So here, take this vector orthogonal to each of them. So we are going to fill this up also by orthonormal vectors Vn. And I'm going to create this matrix. A is is U1, U2, etc. U M and V is V1, V2, etc. V1, V small v1, etc. Vn. All right, now what? So U star is U star, because these are all orthogonal. This is a unitary matrix. So U star is identity. So if I do similarly, V star or V star V is identity. So if I write I can write it as U star A. And this is the same as a summation if you want UI star A. And with the condition that, so this of course I'm going to write summation UI A star UI, just to double transpose. Why I am doing this is because I want to make use of this equation for UI. Look at this. The definition for VA is A star UI divided by multiplied by lambda I. So A star UI is lambda I VI. So I can write here as summation lambda I UI. A star UI is VI star, VI star, I equal to 1 through n, with the understanding that some of these eigenvalues are 0. So if you want, you can write this as. And this is your singular value decomposition. And so what's the moral of the story? So let me summarize this again. So you'd start with any matrix A. From that you create you create A star, find its eigenvalues and eigenvectors, then create the vectors V. So V actually turns out to be the eigenvalues of A star A. Vi turn out to be the eigenvectors of A star A. You can quickly show this because where is the definition of V? VI were defined as, anyway, so this is the, so A star UI will be lambda I UI. So UIs and VIs are the eigenvectors of A star and A star A. And any A, remember this is not a positive definite or anything. Any A can be written in this form. This is very similar to what we wrote earlier. We said any positive definite matrix can be written as a unitary matrix, positive eigenvalues, that same unitary matrix transpose. Look at here. This is not U star. This is a different matrix. So if it is an arbitrary matrix here, this is U lambda. So you can write this as U lambda V star. This is U. This is V. Whereas here, this is U. This is U. If R is non-negative definite. The rest are exactly, so for any arbitrary matrix, you can mimic in this form.
Professor, what's the rank of the, what's the size, the dimension of the eigenvalue matrix?
Well, it depends. I mean, the easiest one is to, so let's say, of course, if A is n by n, everything will be n by n, n by n, n by n, n by n, except as that's the easiest way to see. Because if the sum of the eigenvalues are 0, you will have zeros here. So you may see many ways it may be written. Sometimes people stop here and cut this V to V1 through Vm, etc. Otherwise, everything is, I mean, if this is A is m by n, if this is m by n, then this is m by m, and this will be m by n, this will be n by n. So this will be m by n means m rows and so many columns. But its rank could be even less, so it could be like this. So is it clear? M by m unitary, m by n, n by n. Okay?
Thanks.
All right, now notice you can simplify this further, because even if this is m by n, and the rank of course is going to be less than this size. So rank could be 1, 2, 3, etc. up to some r. So if you want, you can further manipulate this. You can collapse it like this, and then you have to get rid of some columns from here and rows from here, etc. Otherwise, you just leave everything as the size and fill it up with the zeros. So that's the singular value decomposition. And of course, if A is full rank, then A would be n square. Then of course, A can be written as still U lambda V star. So A inverse can be written as then V star, V lambda inverse U star, right? Because V star inverse is V. So this is the same as 1 over lambda I ui Vj star. This is the same as 1 over lambda I ui Vj star. So let's take, since I'm here, I was not planning to go over that, but let's also look at how do you solve this equation? Ax equal to b. A is like this, x is here, equal to b. Anyone? Let's say A is, how do you solve equation Ax equal to b? X is a vector, b is a vector. Anyone? You must have seen. How do you solve 2x equal to 3? Talk to me. Ax equal to b.
And we multiply b by the inverse of a.
So what is x? X equals?
A inverse b.
What if A is not the singular? I mean, A is singular, or A is like this. So there are three cases, right? So this is n by n, A. Here also Ax equal to b. I was not planning to talk about, and the third case is, so let's look at it here. So you have one case, another case like this. And the third case is, so this is n by n, a square matrix. This is m by n, but n greater than m. This is m by n, n less than m. So your solution x equal to A inverse b, what do you mean by A inverse here? So you have these cases to deal with. This is the first thing you should learn. And what you said is A inverse B. This is assuming A is full rank. What if determinant of A is 0? So look at this. Remember, so we can use the SVD to solve all these cases. So A is U. So even if it is full rank, even if it is square, say A is n by n. So then this will be n by n. This will be lambda 1 through lambda n. This will be n by n. This is full rank. So look at here. Ax equal to b. You can write this as u. I'm going to call this lambda. U lambda use v star x equal to b. So I'm going to multiply by u star here. So if I multiply by u star, this is u star. U star u is identity. So you get this expression. Let me call this to be c. So you get lambda v star x equal to c. Remember, c is known because u is known, b is known, a is known. So c is known, lambda is known. So if all the lambdas are non-singular, you can multiply by the inverses. So you can see x will be, first I multiply by the v lambda inverse c. So that's good. This is the case you told me. But you can see otherwise, suppose lambda is like this. Lambda 1, lambda 2, some lambda r plus to 0. And then you have here you have v1 star, v2 star, vr star, rest to 0. I am taking this equation. And then you have x. X is like this. Equal to some vector c. So you see from here you can rewrite this as so you multiply this, you will get a collapsed equation, right? Lambda 1 through lambda r multiplied by v1 star, v2 star, etc., vr star equal to, if everything is consistent, you only need this one, xr star. Now it is easy, right? Because you can multiply by, so let me call this to be D. This is diagonal and full rank, so you can multiply by its inverse. And, oh, there is an x here. And then you have to solve this equation. So remember, this is now this becomes v1 star, v2 star, etc., vr star. This is r by n. N is greater than r because the rank is less than n. So let me call this matrix to be v tilde. So we get v tilde x equal to c1, c2, etc., cr. So I'm going to call this c tilde, this reduced thing. So I can solve for, so I get from here is equal to c tilde. So you get, remember there is a d here. So I multiply by d inverse. So I get this v tilde multiplied by x equal to c tilde with the d inverse. And this one, you can see if I multiply by its conjugate star, this becomes r by r because these are all linearly independent columns. So let me do it in the next line. So I do v tilde x equal to v tilde star d inverse c tilde. This is identity, and consequent, then you get the, or whatever this is, may not be. So then you multiply, by, it's a full rank because it is R vectors. So X turns out to be V star, V tilde inverse, V tilde star, B inverse, C tilde. Everything is known here, that's the point. So this is the best approximate solution. My whole point is you need to know the singular value decomposition to solve these cases. This is called, look at here, few equations and lot of too many unknowns. This is few equations, too many equations, few unknowns. So this is an overdetermined system. This is underdetermined. And if in the underdetermined case, here, I'll write it here itself. In the underdetermined case, if this is a full rank, let's say a rank of A is full, same as its size, smaller size, then you see I can multiply by A star A here. So this is AX, A star AX equal to A star B. Then this is full rank, so I can multiply by C inverse, so I get X to be A star A inverse A star B. So here also the solution is easy, if it is full rank. So the question is, what if it is the question, you can't do that trick here, because this is A star A will be singular. So let me do that case there. So suppose A is like this. This is the interesting case. No, I made a mistake. Look at here. Yes, you are not paying attention either. This I referred to this. So if A is long and short, the fat case, we'll come to it in a second. This is overdetermined. This is easy to solve because you multiply by A star. Yes, so if this is M by N, this will be M by M. So you want this to be smaller. Yeah, so, right, so this is, I was right initially. So this is M by M, and if the rank is, let's say this smaller size is M, but we are putting the condition that the rank of A is same as M, then this will be the solution, which is easy. You don't have to do anything. The issue comes here, because if you multiply by A star here, this blows up to size I'm again getting confused, I guess. See, when you multiply this, you want the A star A to be smaller size. So I guess it is here. Look at here. If I multiply by A star, this will turn out to be N by N. That's what the mistake I made was here. It should be, to both the cases, it will turn out to be N by N. But N by N will be much bigger size. Here it will be smaller size. N by N will be, N is smaller, right? So you have a lot of, so what we are trying to say is that you have a certain number of unknowns, but you made a lot of observations. That's a good case, redundant case, because this is N by N and this is full rank, so you can invert it. Of course, if this is not a full rank, this is not going to work. So the interesting case is this one. So this case is easy because A is here, and let's say this is full rank, by which I mean rank of A is, this is M, this is N. Then when I multiply by A star A, this will be only N by N, and that's full rank, multiplied by X equal to A star B. So X is A star A inverse A star B. Because it is full rank, I can take the inverse. Now, the interesting case is even here it is not full rank, you have to go back to what I did earlier. So let's go to this one. So this is the bad case. So I just gave you the solution. fat, and so that means too many unknowns, too few observations. Too many unknowns. So then you just do as I said, A equal to U. So this may be your case, U lambda V star. So substitute here and simplify, which is what I did for you. So then there will be, that's the best solution you can get in terms of these. So these are the observations, right? This is the model. These are the unknowns. So you made only very few observations. This is just small observations. Because whatever is this size, this has to match. If m is much smaller than n is the number of unknowns. N is the number of unknowns. M is less than n. So then you can plug in the UDV here and solve it as I did in the previous slide. Now to solve one of the homework problems, any questions on this? This is sort of a quick introduction. I also wanted to do, maybe we'll do next Saturday, what is it? So these are the least mean square solutions, but also total least square. Actually, there is a video of me on the YouTube on that, but maybe we can do it next week. I do want to do a little more on the covariance matrix for your homework. So we have I think this may be one of your covariance questions. Two independent stochastic processes. Remember, this will have its covariance matrix Rx positive. This will have its covariance matrix Ry positive. So what is Rx? Rx is things like this, R11, etc., Rij. Rij here is expected value of x of ti multiplied by x of tj star. This is another matrix. I'm going to call it the B11, etc. Let me call this A11, Aij. So Bij is going to be, this is A. Bij is expected value of yt1, yti, ytj star. We know this matrix is non-negative, this matrix is non-negative because they are two independent stochastic processes. Now, interesting thing is, let me take a product of a stochastic process. So this will be a new stochastic process. So let me find the stochastic matrix corresponding to Z. So this is R11, etc., Rij. So if I take Rij, this is going to be expected value of Zti and Ztj star. Look at here, Zt is this, so I'm going to, so this is going to be expected value of xti, xtj star, yti, ytj star. So I can collect all the x terms together, but x and y are independent. So this becomes like this. This is only if they are independent stochastic processes. Then I can take the product of the separate expected values. But look, this is your first Aij, this is your Bij. Aij is from the first stochastic process, Bij is from the second stochastic process. So if but we know that it being a we already proved this earlier. If it is any covariance matrix corresponding to a stochastic process is non-negative, this is non-negative. So the question is, if you look at here, this is interesting. This is looks, so you have a covariance matrix here, which is not the ordinary product. You have these two matrices, RZ, which is this. Then actually you can't write it as a product because product of two matrices is first row into first column. Here it looks like this entry multiplied by this entry. This entry multiplied, because look at here, Rij here is Aij multiplied by Bij. So this is like what you do in high school, whatever, kindergarten multiplication, right? You have two matrices, you multiply element by element. Element by element multiplication. So this is known as, this particular multiplication is known as, product is known as Schur product. So A is Aij matrix, B is Bij. Then if I do this, so this is the Schur product. So this you'll get a matrix whose ijth entry is Aij, Bij. That is not a matrix multiplication, but this is. So that's precisely the case here. So we can write our RZ if you want as Rx Schur product Ry. So we know that Rx is positive, Ry is non-negative. So question is, how do you prove that RZ is non-negative when you have this funny relation? So let me do it for you. This was, I think this is one of the homeworks. So remember, Rx is non-negative definite. That means Rx has the, you can write it as lambda I ui uj star. Some of these lambdas may be 0. Similarly, Ry is, this is non-negative. So lambdas are positive, etc. This I'm going to write similarly mu j, bj, bj star, j equal to 1. Again, some of the mu j's can be 0, but the whole thing is non-negative. And vj can be a complex vector. Now, element by element entry means, remember, this is, if you take each one of them, take one of the entries, lambda I, ui, ui transpose. Remember, this is just a vector multiplied by vector transpose. So this is a matrix whose entry here is lambda I, some u. Remember, this is a vector, right? And this is its transpose. So this is simply, and if I call these entries to be ui1, uin, so this is simply uij multiplied by its transpose, right? So this will be lambda 1 u11 squared. So this will be let's say this is the, we are going to look at the, I don't want to put I everywhere, so I'm going to call this K. So if this is the kth vector, then this is lambda K, UKI, UKJ. But the whole point is these are all scalars. And then let me do a Schur product of this with it's remember, this is just one matrix like this because it's a vector multiplied by multiplied by its transpose. Hold on, let me check something here. Anyway, this is a vector like this. Same thing is true for here. So key to remember is that this is just a 1D vector. You already know the proof, because if you go to the previous section, you can also argue that, where is it here? You can also argue that Z of t came from a stochastic process. So you can say that this is already non-negative definite. So interestingly, that says is that, but the Rij entry of this is coming through this element-wise production. So consequently, you can say that if you define this to be a Schur product where this element-wise. So what we have shown is we know that all the three matrices are positive. So if this is positive, non-negative, this is non-negative, then this is non-negative. So this is because if this is non-negative, this is non-negative, because this is a stochastic process, this is a stochastic process. So this is also non-negative, definite with this thing. That's what I want. So you can argue that, or I'm trying to give you a mathematical proof. So you have Rx, Ry, both are non-negative. Then you do Rx Schur product Ry. So that's going to be double summation lambda I ui this is ui star Schur product summation lambda j. Remember, these are vectors like this. bj star. Now, if this is on I, this is on j. So if you take the summations outside, then you have, remember, this is a scalar, this is a scalar. These entries on each one of them are scalar. So I hope you can see that when you have to just to think about this. This will turn, this is the same as now, this is what you have to show. As I said, this is going to be a vector multiplied vector. So this is a matrix. Then you have a Schur product with a vector multiplied by vector matrix. So this Schur product means whatever is this entry, you multiplied by this. And as I was going to show you, these entries are here. This is lambda k, uki, ukj. Same thing here, a mu k, vk, the corresponding location, vki, vkj. And Schur product means what? We just multiply these two by element. So you will get lambda I, lambda j. And then because of this corresponds to your this lambda k. What I and j are here. But then if you look carefully, this Schur product here, this Schur product, because this Schur product with this is simply multiplying this with this. So this is from a row, this is from a also from a row. So that you can see, if you want, it's the same as ui vj, and then it's a transpose from here. These are with the transposes. So this you have to just numerically convince yourself. So that's going to be ui vj star, because it is scalar entries. Remember, there is no matrix multiplication going on. I'm just doing the Schur multiplication. Then you call this to be some new vector zi. This is another vector. This is zi transpose. So we are back to this. All these eigenvalues are positive, and you have a orthogonal decomposition. So you can also show this way it is positive. You need a little bit more properties on the Schur vector, but essentially this is the way the proof goes. So what is that I have shown? I've shown that if R1 is positive, R2 is a positive matrix. positive, then R, which is the shoe product, is also positive. If these are non-negative, this is still true. Non-negative. I'm going to complete this with we have a little bit time. Any questions? Let me show you an application. So if R is positive definite, remember if 4 is positive, we can write it as 2 squared. Similarly, R also can be written as A squared. How do you do this? So R is positive, can be written as U lambda U star. Lambda is positive, so I can write it as like this. Lambda to the power lambda 1 to the power half, lambda 2 to the power half, lambda n to the power half, lambda 1 to the power half, etc. Lambda n to the power. Because this multiplied by this is lambda. And I'm going to insert here u star u. So I'll do it. So this is lambda half. This is lambda half. So I have u lambda half. Then let me put u star u lambda half u star. But u star u is identity. So now if you look at these three things, if you call this to be A, then this is simply again A. So you can write it, any positive definite matrix can be written as the square of another matrix. So let me show you how to use this, how to solve this. So you said you know how to solve AX equal to B. How do you solve this equation? So this is a matrix equation. Matrix, matrix, matrix equal to matrix. And let me take the case where A is positive, B is positive. So remember, if A is positive, A can be written as C squared. I just showed you here, right? If R is positive, R you can write it as A squared. So you can call the C to be A to the power half, the square root of A, symbolically. But C is really, it's like this, square root of lambda 1, etc. You do the eigenvalue decomposition of A, then this is the way you find A half. So let's go back to this equation. So you have X equal to B. So I'm going to multiply by A half here. So I multiply by A half. I multiply by A half. I multiply by A half. So I'm going to write, I have A half X, A half, X, A half equal to A half B, A half. And because A half is A. But look at this. These two are the same. So I'm going to call this Y. This is some new matrix C. But if B is positive, then B also can be written as, and this is positive. So C can be written as B squared. So you have Y squared equal to D squared. So Y is D. So what is Y? Y is D. D is square root of Y. Right? D is square root of C. So D is A half, B, A half, the whole thing to the power half. I hope you understand this is all symbolic. So now Y is A half, X, A half. So finally multiply by A to the power minus half from here and from the right side also. So that's X. So that's A to the power minus half, A to the power minus half, A half, B, A. So what is A half again? If A is U lambda U star, A half is U, the lambda means lambda 1, etc., lambda n, U star. So the A half means you only do the square root on the lambdas. And A minus half means you, this is 1 over square root of lambda 1, 1 over square root of lambda 2, 1 over square root of lambda n. Of course, this will only work if A and B are positive definite. That's where we start. Then you can solve. Remember, this is a quadratic equation, Riccati equation. Any questions? There is something else called the Hadamard product, but I am not going to. So you have a matrix A, you have a matrix B. What we found was this product is useful. This is Aij, Bij. Remember, AB means you have to, it's a completely different thing. The entry here is Aij, Bjk, right? Or Ajk, Bkj. That's what on the product being on K. But this is a funny product, as the small kids would do. But what we have shown is if A is positive, B is positive, this product is also positive. This product is not positive definite. But there is something else called, so this is known as the Schur product. This is the regular multiplication of two matrices. Matrix multiplication. So if A and B are positive, this is positive, this is not positive. But there is something else called Hadamard product that also comes up here and there. So this is this matrix. A11 is amplified by B. Every entry is amplified by C. So if this is M by N and this is R by S, then notice this. Every entry is multiplied by B. So this will be MR by NS. There is a same theorem goes through. If these two are positive definite, this is also positive definite, but we have to prove it. I haven't proved anything. But you can solve, I just showed you, if you know something, you can solve equations of this type. Now, try to solve this equation. This is the, this comes in control theory. If A and Q are positive, definitely, how do you find this? For this, you can use the, I'm not going to go into all this stuff. Let me do one useful, anybody has any doubt before I go into a related subject? So the important thing I wanted to do was give you an idea about the eigenvalues and eigenvectors of a positive definite matrix or a non-negative definite matrix, and also talked about singular value decomposition. So if A is n by n and the rank less than A, then A can be written as UdV, where U and V are n by n, orthogonal matrices, and lambda would be a diagonal matrix, lambda 1 through lambda R. Any questions? Anyone there? Who is there? Sushant? Kevin? Anyone?
Yeah, Professor.
Okay. Can you hear me?
Yeah.
Anyone, before I go into this, any questions? Talk to me, someone. Students, anybody wants to say something? Is anyone listening?
Professor.
Yeah, is it all clear what I sort of wrote? Anyway, you have the video there, right? Clear enough? So the least mean square goes also. Yeah, so let's look at, so the question is, so this is the question. Okay. So you have some capital, let's say $1 million, whatever. Somebody has some capital, and you want to allocate this into to buy and sell stocks. So this is different. So of course you can use all the money to buy into one, or you can buy. Let's say we decide to put the money into n different stocks. So you have the capital, so you're going to put a fraction into the first one. I'm going to call C1. So C1 is A1C, C2 is A2C, Cn is A and C. So all A's are the fractions. So sigma A will be what? Anybody? Distributing the money, or total money should be equal to C. So sigma A will be equal to? Hello?
Equal to 1.
Yes. So this is all fractions, and all the A's need to be positive, because look here, this has to be some, you're taking part of the money, so that's the A1 is the fraction of the capital. So 10% here, 5% here, 20% here, etc. So what is unknown is how do you distribute the money? That's the problem in portfolio optimization. So of course the goal is to maximize the gain. So let's look at the gain. So if I, let's say you take a stock, ith stock, you are going to buy it at a price SI and sell it at price SI prime. This is the price. So remember, you have, to buy ith stock, you have capital is CI. So the number of stocks you can buy here is CI divided by SI, because this is the price at buying. So CI is AIC, not divided by SI. So when you sell, you get a SI prime, that's the sell price, multiplied by NI. This is the money you get back, CI prime. That's money out. But NI is, where is NI? NI is here. NI is CI SI prime over SI. Right? CI over SI. So gain, GI, just for the ith stock, the gain is money out minus money in. Money in is easy, CI. Money out is here, C is CI SI prime minus divided by SI. So I'm going to pull out CI out. Notice CI is C naught multiplied by AI, SI prime minus SI over SI. But this quantity is the return. Because if you buy it at $2 and you sell it at 3, 3 minus 2 over 1 is 50%. You made 50% gain. So that's what I meant by return on stock SI. But this is a random variable. This is where our course comes in. And so I'm going to call it RI, random variable. So what is the moral of the story? What matters in a stock is not the buy and sell price. The buy and sell price doesn't really matter. What matters is this quantity, the gain, how much money you made. Remember, our goal is to maximize the capital. So this is the gain on one stock. So total gain is going to be gain on all of them. So that's going to be C naught multiplied by summation AI RI, right? C naught AI RI. So remember, RI is the random gain, a random return. So that will be like 2%, 20%, whatever. So let's look at the expected value of G. This is the average gain. And I'm going to call it P is C naught multiplied by summation AI mu I. So I'm going to define mu I to be expected value of RI. So remember, this is the random gain, this is the average gain or average return. 5%, whatever. On the average, you got 5%, 7%, etc. Now remember, this is a random variable, so G fluctuates. G is random. So it has a variance. So we are going to find its variance. So before I do that, if I want G, I can write G as in a vector form. See, A transpose R. Let me define A to be A1, A2, etc., AN, R to be R1, etc., Rn. This is a random vector. So G is, gain variance is G minus so I'm going to call mu G the whole square. So this is G is where? G is A transpose R minus mu then. Squared. So this squared. So that's the same as, so variance of the gain is mu G squared is expected value of A transpose R minus mu multiplied by its transpose R, because it's a scalar, so I can write it as A transpose this way. This is where the randomness comes in. So we are back to a covariance matrix now. Look, R minus mu multiplied by R transpose minus mu transpose. But this is nothing but the covariance matrix of R. I'm going to write it as capital R. So capital R is expected, entry is going to be Rij here. So this is the expected value of Ri minus mu I multiplied by Rj minus mu j. And that is sigma I, sigma j, rho ij. This is the correlation between the stocks, etc. This is a non-negative definite matrix or a positive definite matrix. Let's assume it to be positive definite. So this is where the ideas, so a key idea here is the gain, average gain is going to be whatever it is, but the stock will fluctuate. So remember the unknowns are here A's are the unknown. So I'll summarize here. Average gain is mu G is, what was it? A transpose mu. These are the individual stocks gain and portfolio variance. sigma g squared is A transpose R A. This is the covariance matrix of the stocks that you have picked. So the Markowitz idea, I think this was in the 50s or 60s, is you only control the AIs, right? The fraction of the ones, A1, A2, etc. So you pick these things to minimize this gain, this variance, because you want the variance to be minimize the variance of the portfolio. So this is the portfolio variance. You can call it sigma p squared. So his optimization problem was minimize this subject to this condition. Sigma AI equal to 1. That's the same as saying that E transpose A equal to 1. E is this vector 1, 1, 1, 1, 1 multiplied by A1, A2, etc. AN equal to 1. So let me do that problem and then we'll stop. So we have so remember, portfolio gain is mu p, portfolio gain is A transpose mu. So he is not, take whatever gain you get, but the portfolio variance of the portfolio overall gain is A transpose or A. Remember, everything is real here. A is unknown. So we are going to minimize the variance subject to this condition. Summation AI should be 1. E is the unit vector. E is this. E transpose is just all. This is, you can write this as E transpose A. This condition. So I'm going to divide Lagrange. A modified Lagrange is this. So the unknown is two unknowns, A and lambda. So you take the derivative with respect to A. You should know how to do the vector derivative. I'll just write it here. 2RA plus lambda E equal to 0. Let me put a minus here so it's convenient. So from here you get RA equal to lambda E 2 or A equal to half R inverse E with the lambda here. So to find out this lambda, I can use this condition. So E transpose A will be now lambda by 2, E transpose R inverse E should be 1. So I can solve for lambda. So lambda by 2 turns out to be 1 over E transpose R inverse E. And so you plug it in here. So you have the solution because A is here. So A turns out to be lambda by simply R inverse E divided by. So what's the problem? You say this is no big deal because R is the covariance matrix of this. E is just the unit vector. This means, what does this mean? This means you are simply adding up each row, right? To find out A. A is A1, A2, etc. So look at this. The variance and covariances of the stocks that you started with decides this A. So the big problem here is you have a covariance matrix. When you do the inverse, all the entries may not turn out to be, we want this number to be positive. Whatever is, we want this to be positive, non-negative at least. We cannot have any negative values here. But when you do this may not be true. When you do the inverse, you can have negative values here and there. And if you multiply it by 1 here, this may not turn out, you can have some negative values and positive values. Less than 0 also possible. So that's, so of course you can get luck. If you select a stock such that R inverse has got all the positive entries, then this will be positive. Otherwise, this is the Markowitz solution on the portfolio optimization. If this has negative values, then either you change the stocks or you do a reduced suboptimal optimization. In other words, etc. So you go from there. You can do quadratic programming, linear programming, it goes. But I just gave you the sort of ideas on a fundamental solution to. So conversely, you could say, let me find out a set of stocks so that the inverse of the covariance matrix has got all positive entries. So for example, look at this matrix. Let's say I take two stocks whose variances are 1 and they are negatively correlated. Then R inverse is going to be, you know, the determinant is 1 over 1 minus rho squared, right? Divided by this rho. See, in this case, R inverse has all positive entries because, that means these two stocks are negatively correlated. So if you use two negatively correlated, then remember R inverse E. E is in this case this. So the solution turns out to be 1 plus rho divided by 1 minus rho squared. So that means you put 1 minus rho. So that means if you have two negatively correlated stocks, you put your money equally into the two stocks to minimize the variance. That's what the optimum solution is. Now, if you can find 3 by 3 stocks where the inverse turns out to be positive, then this will be a positive solution. And if you can find out 10 of them, then the inverse is positive, then you'll get that's one way to go. I am sort of done. If anybody has any questions, I'll otherwise maybe next week I can talk about this problem maybe in little more detail. So many cases you have a square matrix, or A could be square, but then A could be lower rank, R equal to n, R is less than n, or A could be like this, m n. Here also two cases, the rank is equal to n, and or R is less than n, A equal to this way, m n, rank equal to m, rank less than n. So these are the worst case. This is the worst case. This is the worst case because too few equations, too many unknowns, and even the equations we have are not reliable. The rank is less than n. So I'll talk about this. So the way is we at least mean square solution. There is also something called total least mean square solution. So let me sort of read up on it and then we can discuss it tomorrow, because as a graduate student, this is the bare minimum you should, and the solutions will involve a singular value decomposition of A. So that's where I want you to sort of come prepared next time, or at least to read up on read upon what I just described, the SVD, and then come over, then we can look at this solution next week. Any questions? Otherwise, I'm going to stop here. Anybody?
Oh, so Professor, in order to approach to the recording video, should I go through the NYU classes and to check out the content?
Right. Let me stop the video. Hold on.